Oh, Mr. Long, this is FRQ number 3. So it's a block of mass m equals 5 kg initially moving with an initial speed vi at t equals 0, travels down a rough incline as depicted below. The velocity time graph corresponds to the block's motion from the top of the incline to where it comes to a halt. So part A asks for the block's average speed for the entire time interval shown in the graph. So basically, we know that S average is equal to distance all over time. Now the distance in this case we can find using the graph, and to find using the velocity time graph is basically the distance is the absolute value of all the areas added up. So see, from 0 to 3 we can split up into two things, a triangle and a rectangle. From 3 to 5 that's a square, 5 to 7 is the triangle. So it'll be 1/2 times 2 times 3, because it'd be 1/2 times, this is your length, your 2 and 3 length times and width, plus 2 times 3, that's the rectangle from 0 to 3, plus 2 times 4, plus 1/2 times 2 times 4. And you have is equal to 3 plus 6 plus 8 plus 4, which d is equal to 3 plus 6 plus 8 plus 4 is equal to 21. So we know our d is 21. Time, we can look for the whole interval. It takes 7 seconds on the graph. So S average is equal to 21 divided by 7. So S average is equal to 3 meters per second. Okay, part B. It asks to calculate the coefficient of kinetic friction during the flat segment of the ramp and the block. Oh, during the interval, sorry. T equals 5, 7. So we're basically looking at this area. So from there, we know that since there's no force on it, we know that net force is equal to frictional force, because there's no other force acting upon it at that moment. We also know that net work is equal to net force times the displacement, the parallel displacement. And then from here we know that displacement from 5 to 7 is just this triangle here, so it'll be 1/2 times 2 times 4, which is displacement is for this section is equal to 4. And then from here we also know that net work is equal to the change in kinetic energy, which is equal to 1/2 times mvf squared minus 1/2, my bad, 1/2 mvi squared. And then we just cancel this one out because at the end there's velocity 0, so we just have vi, so it'd be net work is equal to negative 1/2 mvi squared. So net work is equal to, just plug in the values we know. I keep on hitting that, my bad. 2, and then mass we know is 5, and then vi we know is 4 because you're asked to find that segment, and it starts at 4 squared. And that net work is equal to negative 40. So then from here we know that, as mentioned before, net work is equal to net force times your displacement. So net force times displacement x is equal to negative 40. But like I said earlier, so Fk is equal to your net force because that's the only force acting upon it during that segment. So we can say Fk times displacement x is equal to negative 40. As mentioned earlier, displacement x is 4, so it's equal to negative 40. Basically isolate for Fk. Fk is equal to negative 10 n. We're not done there yet though, because we're asked to find the mu k. So then mu k we know is equal to Fk divided by Fn. we know what FK is, but we need to find what FN is. And in this case, FN is equal to mg, and it is because, as you can see here, it's on the flat surface, it's not on an incline, so it is equal to mg. So then Fn is equal to 5 times 9.8, which Fn is equal to 49. So from there, we just plug in our values. Mu k is equal to 10 divided by Fn 49. So mu k is equal to 10 divided by 49. Put my calculator is 0.20. And then here we don't have to have negative 10 because UK is a scalar, or not scalar, just it has no direction and no units. So yeah. Okay, that's part B. Okay, part C. Part C asks to calculate the coefficient of kinetic friction, one between the surface of the ramp and the block. So we're asked to find this part right here. So then for part C, we, as mentioned before, we know that net work is equal to displacement KE. So we know that it is equal to 1/2 mvf squared minus 1/2 mvi squared. And then from here, it starts at 2, as we can see from the graph. So we know our vi is 2, and here it ends at 4, because from here, it doesn't accelerate anymore. So that means at the end right here, that's where it stops accelerating. So we know that its VF is 4. So you go to 1/2, and the mass is 5, 4, VF 4 squared minus 1/2, 5 times 2 squared. So net work is equal to 40 minus 30. So net work is equal to 30 joules. And then from there, as mentioned before, we know that net work is equal to your net force times displacement x. In this case, displacement x is basically this triangle and rectangle here. So it's equal to 1/2 times 3 times 2 plus 30 times 2. So that is displacement x is equal to 30 plus 6. So displacement x is equal to 9. So from here, we know that net force, find what net force is. Net force is equal to Fgx minus Fk is Fgx because it's on an incline. Right here. And since on incline is you're gonna have a triangle, or kind of like a triangle, it'd be like this is a reference angle, and then the boxes are right here. It'd be like, yeah, and then this is Fgx parallel to its displacement. Alright, so we know that Fgx is equal to Fg sine 30 minus Fk, or not minus, okay, just the 30 part, but that's, yeah. So then, yeah. We plug in the values we know. It's equal to 5 times 9.8 sine 30 minus Fk. Oh, before I mentioned, Fg is just basically mg, so that's why we can plug in 5. This simplifies to 24.5 minus Fk, and that is what your net force is equal to. From there, we can basically plug it back into this equation. So we know that 30J, or I'll just write unit list for now, is equal to 9 times 24.5 minus Fk. The 9 comes from the displacement. We basically just isolate for Fk. So 30 divided by 9 is equal to 3.33. It's equal to 24.5 minus Fk. And then we basically isolate for Fk. Minus 24.5 negative 21 divided by 21.5 0.17 is equal to FK. But we're looking for mu K, and then we just need, as mentioned before, mu K is equal to Fk divided by Fn. In this situation, Fn is a little different because it's on an incline, so then Fn is equal to Fgy, and Fgy is equal to mg cosine 30. And then it'll be plugging in the information we know. g is a constant, 9.8 times cosine 30, which is equal to 42.44. And then that's what our Fn is equal to. From here, we can just plug it into here. Fk and Fn. K is equal to 21.17 all over 42.44. So mu K is equal to 0.50. And then, like mentioned before, mu K has no direction and no units. Okay, that's part C. Part D asks for the initial mechanical energy of the system at t equals 0. So in part D, okay, so MEI at that point is equal to the potential energy initial plus your kinetic energy initial, which is equal to mghi plus 1/2 mvi squared. PEI is equal to mghi, KEI is equal to 1/2 mvi squared. So we know everything except HI, but we can find HI because it's just at this point we know we can find height. So we know that sine 30 is equal to h over d because using trig functions, it's the angle is right there, and then sine is opposite over hypotenuse, and the hypotenuse is just distance or displacement I should say, and your displacement in this area is equal to 30 times 1/2 times 4 plus 30 times 2, which is equal to 9. So it'd be sine 30 is equal to h over 9. Isolate for h, so it'll be multiply 9 to both sides is equal to h. So h is equal to 4.5. Or I should say h initial is 4.5. So from there, we have all the information we know now. So MEI is equal to 5 times 9.8 times 4.5 plus 1/2 times 5 times times 2 squared. And that would equal to 230.5 joules. So that's your initial mechanical energy. Okay, part E. Okay, it asks to calculate the net work done on a block as it accelerates down the ramp using both methods. So we'll start with this method first. Net work is equal to net force times delta x. So, so we know that net force down the ramp, there's friction, so it's equal to Fgx minus Fk. Using what we found in a previous part, we know that Fgx is 24.5 and Fk is 21.17. Excuse me. So we know that net force is equal to 3.33. And then as other parts, we know that displacement at this point is equal to, like here, is equal to 9. So basically, we know that net work is equal to net force. It's net force times displacement, so we do 3.33 times 9. So net work is equal to 3.33 times 9 is equal to 29.97 joules. All right. Now we find it using method 2, which is net work is equal to change in KE, which we can write change in KE as 1/2 mvf squared minus 1/2 mvi squared. We know, as mentioned before, that at the end of the incline ramp, its final velocity is 4, and at the beginning of the incline ramp, it starts with initial velocity of 2. So using that, we can plug in our values. 5.4 squared minus 1/2 times 5 times 2 squared. And plugging that in, we will get 30 joules. And then, as you can see, using both methods, they're basically the same. They just have, since they're different methods, and one of them involves a lot of rounding, or it could involve a lot of rounding. There is a little bit of that rounding error, but then they're basically the same because if you round this one, it is basically 30. Okay, part E, part F now, the final part. It basically asks how would the following quantities behave during the incline segment if the mass is doubled to 2m. So for A, your frictional force, Fk, would increase. And that is because if you look over here, when we found Fk during the incline segment, we involved the use of mass. So yeah. So if your mass increases, your Fk will also increase. Okay. B, acceleration. Acceleration will stay the same because, as we know, that if this incline, it's to find acceleration would be doing, because we know that net force is equal to ma, and we also know that net force is equal to fgx minus fk, and we know that fgx and fk would have an m. If we were to equal them together, it would be mg sine theta minus mu k mg cosine theta is equal to ma, and we solve for a. We would just isolate for, we could factor out m, so it'd be g sine theta minus mu k g cosine theta is equal to a. We just multiply, divide by m and m. You can see that m does not factor in at all when it finds acceleration. So even if your mass is doubled, it wouldn't affect acceleration at all. Okay, C. It would increase, your work Fg would increase. That's because your work Fg is equal to your PEI, initial potential energy, which is equal to mghi. It has an m, so if your m doubles, it means this would also increase. That is FRQ number 3.